Elliptic curve cryptography explained. Elliptic curve cryptography is a type of asymmetric or public key cryptography based on the discrete logarithm problem as expressed by addition and multiplication on the points of an elliptic curve. Bitcoin uses a specific elliptic curve and set of mathematical constants as defined in a standard called SECP 256K1, established by the National Institute of Standards and Technology, NIST. The SECP 256K1 curve is defined by the following function, which produces an elliptic curve. Y squared equals x to the third power plus 7 modulo p. The modulo p indicates that this curve is over a finite field of prime order p, where p is a very large prime number, close to 2 to the 256th power. Because this curve is defined over a finite field of prime order instead of over the real numbers, it looks like a pattern of dots scattered in 2 dimensions, which makes it difficult to visualize. However, the math is identical to that of an elliptic curve over real numbers. The SECP-256K1 Bitcoin elliptic curve can be thought of as a much more complex pattern of dots on an unfathomably large grid. In elliptic curve math, there is a point called the point at infinity, which roughly corresponds to the row of 0 in addition. On computers, it's sometimes represented by x equals y equals 0, which doesn't satisfy the elliptic curve equation, but it's an easy separate case that can be checked. There is also a plus operator called addition, which has some properties similar to the traditional addition of real numbers that grade school children learn. Given 2 points, P1 and P2 on the elliptic curve, there is a third point, P3 equal to P1 plus P2, also on the elliptic curve. Geometrically, this third point P3 is calculated by drawing a line between P1 and P2. This line will intersect the elliptic curve in exactly one additional place. Call this point P3 prime equal to x comma y. Then reflect in the x-axis to get P3 equals x comma negative y. There are a couple of special cases that explain the need for the points at infinity. If P1 and P2 are the same point, the line between P1 and P2 should extend to be the tangent on the curve at this point P1. This tangent will intersect the curve in exactly one new point. You can use techniques from calculus to determine the slope of the tangent line. These techniques curiously work, even though we are restricting our interest to points on the curve with 2 integer coordinates. In some cases, i.e., if P1 and P2 have the same x values but different y values, the line between P1 and P2 will be exactly vertical, in which case P3 equals point at infinity. If P1 is the point at infinity, then P1 plus P2 equals P2. This shows how the point at infinity plays the role of 0. It turns out that plus is associative, which means that A plus B plus C equals A plus B plus C. That means we can write A plus B plus C without parentheses and without ambiguity. Now that we have defined addition, we can define multiplication in the standard way that extends addition. For a point big P on the elliptic curve, if small k is a whole number, then small k times big P equals P plus P plus P k times. Note that k is sometimes confusingly called an exponent in this case. Generating a public key. Starting with a private key in the form of a randomly generated number small k, we multiply it by a predetermined point on the curve called the generator point big G to produce another point somewhere else on the curve, which is the corresponding public key big K. The generator point is specified as part of the SECP 256K1 standard and is always the same for all keys in Bitcoin. Big K equals small k times big G, where small k is the private key, big G is the generator point, and big K is the resulting public key. a point on the curve. Because the generator point is always the same for all Bitcoin users, a private key small k multiplied with big G will always result in the same public key big K. The relationship between small k and big K is fixed, but can only be calculated in one direction, from small k to big K. That's why a Bitcoin address derived from big K can be shared with anyone and does not reveal the user's private key, small k. Tip: a private key can be converted into a public key, but a public key cannot be converted back into a private key because the math only works one way. Implementing the elliptic curve multiplication, we take the private key small k generated previously and multiply it with the generator point big G to find out the public key big K. Big K equals 1e99 AEDD times big G. Public key big K is defined as a point big K equals x comma y, where x equals f028 y equals 07cf 5bdb. To visualize the multiplication of a point with an integer, we will use the simpler elliptic curve over real numbers. Remember, the math is the same. Our goal is to find the multiple, small k times big G, of the generator point big G, which is the same as adding big G to itself k times in a row. In elliptic curves, adding a point to itself is equivalent of drawing a tangent line on the point and finding where it intersects the curve again, then reflecting that point on the x-axis. The diagram in the book shows the process for deriving big G, 2 times big G, 4 times big G, and 8 times big G as a geometric operation on the curve. Tip: Bitcoin uses the SECP 256K1 optimized C library to do the elliptic curve math.